Hello everyone and welcome. In this video we're going to look at implicit differentiation. Specifically we're going to review the concepts of implicit differentiation that you would have learned in your Calculus 1 course. After that we're going to do implicit differentiation with Mathematica. And finally we're going to verify our results graphically also using Mathematica. So let's get started. So first we'll consider the equation y minus x squared equals 1. Now this is a really nice equation because we know that we can solve this for y. We can solve it for y and then express it as y equals some function of x. So we can write this as an explicit function of x. And that's really nice. That lets us work with this equation a little easier. For instance, we'll be able to plot this function with Mathematica by using the plot command. The first argument to the plot command is actually that function. Since we can solve for y, we can find that function. The other thing we can do is calculate the derivative easily. We can just solve our equation for y, and then we know how to calculate dy dx. We can do all this because we have this equation which can be written explicitly as a function, which means for every input x, there's exactly one output y. What if we look at a different equation? Consider the equation x squared plus y squared equals 1. This one's more challenging. If we tried to solve this for y, we'd end up with plus or minus the square root of something. In other words, for each input x, we might get more than one possible y value. But this says we can't solve this for y and express it explicitly as a function of x. We can still talk about x being an independent variable and y being a dependent variable, but we can't solve this equation explicitly for x. So that makes it a little more challenging to work with. Now you learned earlier in this module that we can still visualize this equation, this curve. We can plot it using the contour plot command. The first argument of the contour plot command is actually the full equation that we're working with. And then we just specify a range for x and a range for y. And so we can actually see an example of this right here. So here we have the example of the contour plot, and you can see that if I put in certain x values, I'd possibly get two different options for outputs y. Now if we look at this plot though, we can see that it is just a curve, and so I should be able to go to any point on this curve and generate a tangent line. And that tangent line would have a slope. So I expect to be able to calculate the slope of the tangent line, but if I can't solve my equation for y, how do I calculate dy dx? Well, the answer is we'll use implicit differentiation. So, given our equation x squared plus y squared equals 1, to calculate dy dx, what we'll do is calculate the derivative with respect to x of the entire equation. So the derivative of the left side equal to the derivative of the right side. Now on the right side, that's not too bad. Well, the derivative of a constant with respect to x, that should be 0. The left-hand side, we have the derivative of a sum, so we can break that into the sum of the derivatives. So we can write that like this. And the first expression is just a function of x, so if I take the derivative of x squared with respect to x, I will get 2x. But this next one is a little bit trickier, because even though we can explicitly solve this equation for y and write y as a function of x, here we're still treating x like the independent variable and y like the dependent variable. Which means when I take this derivative, I really have to use the chain rule here. And to do that, I would say the derivative of something squared is 2 times that something times the derivative of the inside piece. So this would generate dy dx here equal to 0. The big idea is y depends on x. So we can really think about it in that form. Now once I have this expression, now that I've taken the derivative with respect to x, I really want to find out what dy dx is. That's what I'm trying to find. So all I have to do is solve my equation for dy dx. In this case, I will just subtract 2x to the other side, and then lastly I would just divide through by 2y. And the result will be negative x over y. So in this case, I have an expression for dy dx, and so I could look at any point that's on my circle and plug in the associated x and y values and find the slope of the tangent line at that point on my circle. So what we've seen here is my first step was to take the derivative of the entire equation, and after that it was to solve for dy dx. Now let's take a look and see if we can do that in Mathematica. Alright, so here we have a list of our steps. We're working with the curve x squared plus y squared equals 1, and I want to first take the derivative. Now normally if I had an equation I could solve for y, I'd solve it for y, and I'd define a function and then use the prime notation. But in this case we can't do that, so we'll have to use the d command to take the derivative. We'll put in the full equation, so that's x squared plus y squared equals, with a double equal sign, 1. And we want to take the derivative of that with respect to x. So our syntax is the thing we want to take the derivative of in the first argument, and then with respect to what variable in the second argument. So if I just leave it like this and run this cell, it will generate a derivative, but it's not the value that I calculated earlier. Something's gone wrong. And if I look at the output, it looks like it's taken the derivative of x squared to get 2x, but when it tried to take the derivative of y squared, it just got a value of 0. And the reason for that is that Mathematica does not know that we want y to be a dependent variable and to depend on the value of x. If we want that, we need to explicitly tell Mathematica that this y right here is actually a dependent variable and it depends on x. So when we're trying to do implicit differentiation in Mathematica, we have to explicitly type the dependency of the variables. So if I put that dependence of x on there, and now I rerun this cell, now I get the value I expect. Now I have my 2x plus my 2y times dy dx, or y prime in this notation. So now it really has taken the derivative implicitly. So my next step would be to solve this for y. Now I could certainly, if I wanted to, just copy that output, paste it down here, and then my goal is to solve this equation for what? For y prime of x. So the solve command works by putting the first argument as the equation I'd like to solve, and the second argument is what I'd like to solve it for. So now if I run this cell, it will find my solution. In this case, it's negative x over y. So another way I could do the same process is that up here, this command has calculated the derivative, and the output is the equation. And so I know that it'll always do that, so what I could do is actually wrap that solve command around the entire derivative command, just like this. And in that way, I can actually have one line of code that would kick this out. Either way, of course, is totally fine. Alright, so now we have our expression for y prime, the slope. Now the next thing I'd like to do is actually work with this a little bit and hopefully verify my results graphically. So to do that, I'm going to want to store my result for dy dx here as a function that I can actually use to calculate specific slope values. So I'm going to create a function that I'm going to call derivative. Derivative is going to be a function of two variables, x and y, and it's going to be my calculation above, negative x over y. Now notice in this context, I didn't put negative x over y of x. I don't have to put that dependence relationship here, because here I'm really calculating the derivative as my dependent variable, my result, and it depends on the values of x and y that I put in. Alright, so here's my derivative function. I can run that. And so that means that what I can do is I could calculate the derivative at different points. As long as I just plug in some values here, I will find the slope at that spot. Let's try a different one here. Let's try 0, 1, for instance. Okay, now to see if that makes sense, let's plot this equation. So to do that, once again, we have to use the contour plot command, and then we'll put in our equation, x squared plus y squared double equal sign 1, and we'll plot this over a range of values. I'm going to type in x and y both go from negative a to a, and then I will just let a equal 1.5. That's a value that seems to make sense since my curve, my equation, is a circle of radius 1. So I'll run that and I'll generate my curve here. And notice I've calculated the derivative at the point 0, 1. Well, if I go to the point 0, 1, that would be up here. I can see the slope really should be 0. And earlier, when I calculated the value derivative of 1, 0, I got this. That also makes sense, because if I went to the point 1, 0 over here, the tangent line would be vertical. And so I would have an undefined slope, which is exactly the value that gets kicked out. Let's try one more value. If I went maybe 45 degrees around my circle right to about here, well, that point would be the point 1 over root 2 and 1 over root 2. So I'm going to put those values in here as well. Oops, root 2, there we go. And I have a value of negative 1. And sure enough, if I went to this spot, I can see the slope might be, it's definitely going downhill, definitely negative, so negative 1 seems to make sense. Now, if I really wanted to verify that, another thing I could do that we've done before is I could actually plot the tangent line at that point. So how would I do that? Well, let's see. The equation for a line in point slope form would be y minus y sub naught equal, double equal sign in Mathematica, the slope times x minus x sub naught. So that's my general equation. Now to find my values. Well, the slope that I want is exactly this derivative value. That should give me the slope at that point. And the x sub naught and the y sub naught values are the points on the circle. So if that's my x coordinate, I can just replace x sub naught with that x component of my point, and I can replace y sub naught with the y value at that point. Alright, so now I should really generate the slope of that tangent line. I'm going to go ahead and run that cell. I can see that it defines my slope and also gives me my line. Now I could certainly solve that equation for y, but I actually don't need to. I don't have to actually solve it explicitly for y if I want to use contour plot to plot it. So I can actually just take that result right there and throw it into my contour plot to plot two functions, a list of not functions but equations, curves, and there I can see that really is the tangent line. Alright, so all in all for this video, we have reviewed implicit differentiation, we've done implicit differentiation Mathematica, and we verified our results graphically. And that concludes this video. Thank you.